Good morning, students. Mr. Carver here. Today we're going to do section 2.6. It is called related rates. We'll get to that in just one moment. I'd like you to work this warm-up problem, if you would, please, from section 2.5. You can pause it now. Hit play when you're ready to go over it. All right, you need two things to find the equation of the line tangent to a curve. The first is the point. We have that. That is at the point 2, 2. We also need the slope. In order to find the slope, what I'm going to do is find the slope machine of my point machine, and that is by deriving first the left-hand side with the product rule. The product rule works. You do not derive one, and you derive the other. It is 2y dy dx, and that is then plus then the derivative of the first, which is -1, times the second as is, and that is equal then to 3x squared. All right. You've got your slope machine here. At the point 2, 2, you can find the numeric value of the slope by plugging in that point into my slope machine. So let's do that now. And that gives you that line right there. And then we're just going to put this all together using PEMDAS. So I've got 2 times 2 times 2. That is 8 dy over dx. That is minus 4 is equal to 12. So I get 8 dy over dx. I'm going to add 4 to both sides. That's equal to 16. So my dy over dx is equal to 2. That is a slope at the point 2, 2. There's too many 2's in this problem. So here we go. The equation of our line tangent to the curve at the point 2, 2 is y minus 2 is equal to 2 times x minus 2. Not easy to read, but that's my answer right there. All right. All right, students, section 2.6 is related rates. And what we do is we pick up where we left off in section 2.5 with implicit differentiation, and we apply it to some real-world problem solving. So I think I mentioned this in class the last few days. If you have something like this, 2x plus y squared is equal to 16, and I wanted to derive that with respect to x. Here's what you do. You derive y's and x's using exactly the same rules, but you follow it with d of that letter over dx. And here's what I mean. If I derive 2x, I get 2, but according to what I just said, I'm going to follow that with dx over dx. I'll then add that to 2y dy over dx, and that's equal to 0. It's this statement right here and this statement right here that's going to tie into section 2.6, and that is the rule that says no matter what you derive, what letter you derive, you follow it with d of that letter over dx when you are deriving with respect to x. But in section 2.6, we're going to be deriving with respect to time. So the same rules apply, but if I back up then to my original equation here, 2x plus y squared is equal to 16, and I derive that now with respect to time, here's what I'm going to get. I'm going to get 2 dx over dt, and time is represented by the variable t. I'll add that then to 2y dy over dt. And of course, 16 then goes to 0. So if you follow this step right here, deriving any variable with the same rules that you applied to the x's, but following it then with d of that letter over dt, that's really the skill that you need to utilize in section 2.6. So let me give you an example of the types of problems we're going to be working in 2.6 right now. All right, here's a problem. You can pause this and get this written into your notes. You got a spherical balloon is being filled at 10 cubic centimeters per minute. Find the rate at which the radius is increasing when the radius is 2 centimeters. All right, so let me give you some steps that you're going to use to solve these. We're going to follow these steps for every single problem that we do in this class. And then I'll work through this problem utilizing those steps. All right, so here we go. All right, so step number 1 is to identify all the quantities given in the problem. That is the quantities given and those that are desired or asked for in the problem. So in this problem, what we're given is 10 cubic centimeters per minute. So we are given in this problem that quantity right there. And if you think about what this represents, 10 cubic centimeters represents the change in volume. Now, from a calculus standpoint, I'm going to call that dV, that is the change in volume. Just like slope is dy over dx, that is change in y over change in x, this is going to be change in volume over the change in time. So that is dV over dt, literally the change in volume over the change in time. And what I want is identified in this sentence right here. Find the rate at which the radius is increasing. So what I'm looking for then is the change in the radius, that is dr over time. So I'm looking for the change in radius over time when r is equal to 2 centimeters. All right, so that's step one. And step two then is to relate those quantities with an equation. Now, it's not the time that you're trying to relate. What you're trying to relate is volume to radius. So it's volume to radius. Now, I realize I'm not going to have you memorize all of these formulas. We're dealing here with a spherical balloon. Most of these formulas are either given in the problem or they can be found in the front cover of your book or the back cover of your book, depending on which edition we have, that you have, rather. So what I'm looking for then is the volume of a sphere in terms of r. So let's go ahead and do this on the next page here. The volume of a sphere turns out to be 4/3 pi r cubed. And again, I'm either going to give you that on a test or a quiz, but for the homework, you can find it in the front cover of your book. Volume is equal to 4/3 pi r cubed. So that's step two. Step three then is this. You want to derive the equation that relates those two variables, and again, that is your r and your v. You want to derive implicitly with respect to time, and that's the rule I talked about on the first screen here. So let's go ahead and go through that now. If I derive this equation with respect to time, again, the rule is you derive every variable with the same rules as you use for x's, but you follow it then with d of that letter over dt. So let's go ahead and go through that now. V turns out to be 1 dv over dt. And on the right-hand side, I'm going to use the constant multiple rule because 4/3 pi is a constant. And then I want to derive, rather, the r term. So that's going to be 3r squared. And I want to follow that with dr over dt. Because, again, that's the rule. You derive any variable just like you would normally. You follow it with the d of that letter over dt. Cool. We can clean this up here a little bit. I can cancel these 3's. And that brings us then to our last step. And the last step is this. Substitute and solve. It's very, very important that you do not substitute until the very final step. If you substitute too early, you're going to have too many constants in your equation, and when you derive them, they're going to go to 0, and you will have nothing to work with. So I'm going to take this equation right here. I'm going to substitute in my constants, and I'm going to solve. So let me just write down the cleaned up version. I got dv dt is equal to 4 pi r squared dr over dt. And what can I substitute in? Well, first of all, I know that dv dt is, if I look back to my original equation, 10 cubic centimeters per minute. So this is going to be 10. I've got 4 pi, and my r is right here. It's 2 centimeters. So 2 goes in there. I'm going to square that. And dr dt is the change in radius over time. This is what I'm solving for. So what I want to do is grab my calculator, and I'm going to take 10, and I will then divide it by 4. Then I'll divide it by pi. Then I'll divide it by 4 again. And it will bring me this answer. dr over dt should be equal to 0.199, and that is going to be in centimeters per, let's just go back and check this. This is centimeters per minute. This is a linear rate of change. It is the change in radius per minute. All right, let's do a second problem here. You've got a baseball diamond. Let's see if I can draw this. All right. And I don't expect you to know this, but the baselines are 90 feet. And what you have is a runner running from first to second base. You've got a base runner running from first to second base at 10 feet per second. That's my amazing drawing there. Let's put a baseball hat on him. The question is this: how quickly will the distance from home plate to the runner be changing when he is halfway to second base? All right, so again, you've got a guy running from first to second base. I'm looking for how quickly the distance from the runner to home plate, that's this distance right here, is changing when he is 45 feet from second base. All right, so here's how I'd like you to approach this. If you take a look at this triangle right here, that is going down the first base line to the runner, and then from the runner to home plate, what you have is a right triangle here. And so what you're looking for then is you're looking for the two changing quantities that you are either asked about or that you are interested in. So first of all, I know something about the rate at which this side right here is changing. That is from first to the runner, and that is going to be increasing at the rate the runner is running from first to second base. So stick with me here just for a second. This side right here I'm going to call X. You can call it whatever letter you want. I'm then asked about the rate at which the distance from the runner to home plate is changing. I'm going to call that Y. And again, you can call it whatever letter you like, but that then allows me to start the steps for solving this problem. So step number one, again, I want to set up or write down the quantities that I am given. And I am given, in this case, the rate at which x is increasing. And if you recall, in calculus, we call that dx dt. That is literally the change in x over time. That is going to be 10 feet per second. I am looking for the rate at which y is changing, so I'll call that dy over dt. And I'm looking for that when x is equal to 45, because it's halfway to second base. So again, I'm focused on just x and y in that picture. So that's step one. Step two then, I want to relate it with an equation. And since I'm using a right triangle here, I hope it makes sense to you that I'd be using the Pythagorean theorem. So I've got x squared plus y squared is equal to 90. That's wrong. That's completely and utterly wrong. So I've got x squared plus 90 squared is equal to y squared. Remember, y is the hypotenuse. So that's step two. That's the equation that relates the two quantities. Step three, then, what I want to do is derive implicitly with respect to time. So 2x squared, rather, goes to 2x dx over dt. Remember, no matter what letter you derive, you follow it with the d of that letter over dt, plus 0 is equal to 2y dy over dt. So now I've got step two completed. And now, if you recall, the final step is to substitute and solve. Make myself a little room here. So step four then, I'm going to substitute and solve. So I've got 2. I know my x is 45, and dx dt is 10. And now the problem on the other side is this. I'm looking for dy over dt, but I don't have y. I need y in order to be able to solve for dy over dt. So what we're going to do is we're going to look back somewhere on our paper for an equation that relates x to y, and I'm going to find it right here. So I can now solve that for y. So I've got 45 squared plus 90 squared is equal to y squared. So my y turns out to be, when I square those and add those together, the square root of 10125. So that's going to go right here. And now all I have to do is just divide through by 2 times the square root of 10125, and that will give me my answer. So let's get rid of some of this stuff. And that gives me an answer of dy over dt as 4.47. And I want to use the same units of measure that are given in the problem. So this is going to be feet per second. 4.47 feet per second. All right, my people. Hopefully that'll get you through the first 2 assignments. And I will be back next week and answer questions to get you guys caught up. Thanks much.